Let's look at one more example. This comes from number 10 on your worksheet. So it says a 150 Newton body is allowed to slide down a frictionless inclined plane 2 meters high and 10 meters long. Question A says how much kinetic energy will the body have when it reaches the bottom of the plane? And B, what will its velocity be? So first off, let's draw this situation. So we have an inclined plane here. We've got an object sitting on it. That object is 150 newtons, so that is your Fg right here. Fg equals 150 newtons. The inclined plane is 2 meters high, so from here to here is 2.00 meters, and 10 meters long. So I would read that as this being 10 meters. How much kinetic energy will it have when it reaches the bottom of it? So we're asked to find KEF. Is there anything else we know? I don't think right now. So let's see if we can figure this out. So what do we know? Let's look at this. We're looking for kinetic energy final. What about our potential energy at the final? So once it reaches here, it doesn't have any further to drop, so any further from our reference point to drop, so its potential energy is 0. Well, let's do the same thing up here. What is its potential energy initially, and what's its kinetic energy initially? Well, one of those we already know. The kinetic energy, when it starts, is 0 because its velocity is 0. What about its potential energy? We can calculate that, mgh, and we'll call that the height initial. So the mass, do we actually know the mass? No, we don't. We know Fg though, which, what do we know about Fg? Fg is just mass times the acceleration due to gravity, which is this part right here. This is really just Fg. So this is 150 newtons. Let me be even more clear. This part is 150 newtons. And the height initially was 2.00 meters. So that gives me 300 newton meters or 300 joules. So if this is frictionless, which it said it was, are we going to lose any energy due to heat? No. There's no friction, so we're not going to have any loss of energy due to friction. So we know that the energy initial, the net energy initial, should equal the net energy final. So in this case, my net energy initial was just, since kinetic energy is 0, it's just my potential energy initially, right? And my net energy final, we know it's these two added together, but this one's 0, so it's just my kinetic energy final. We actually know what this is. It's 300 joules. We calculated it, and this is what we were looking to find, the kinetic energy final. So there we go. There's my answer. What was its kinetic energy final? 300 joules, and this was because of the conservation of energy. And we didn't have to worry about any friction, so we knew that this setup is good. So that's actually my answer for question A. Question B asked us, how fast is it going? Well, now that we have kinetic energy final and there's no friction slowing it down, it should just accelerate pretty nicely. We don't know acceleration though, do we? We could use a kinematic equation. We could break this up into its component forces, so we'd figure out what the force was going parallel to this, and we could use that to figure out our acceleration, and then use a kinetic equation to find out what its velocity was, Vf is. Or we could do it much simpler and do an energy calculation. We know that KEF is equal to 1/2 mvf squared. And we know a lot of this stuff, right? We know that this equals 300 joules. So if I just rearrange this for Vf, so Vf equals 2 times the kinetic energy divided by the mass, all square root. So that's just rearranging this for Vf. We can fill this in now. We have 2 times 300 divided by the mass. We didn't calculate that yet, so we actually do need to go up and calculate the mass here. So we can do that from this question. So we know, we'll just do it in black over here. Fg equals m times g. M would be Fg divided by g. So Fg was 150 newtons divided by 9.81 meters per second squared. That gives me 15.3 kilograms. So we can just plug that right into here, 15.3 kilograms. So if I do 2 times 300 is 600 divided by 15.3, and then take the square root of that, that gives me a final answer of 6.26 meters, meters per second. And there's my final velocity. No need to use a kinematic equation, no need to break up any forces into their components. We were just able to do an energy calculation to get that final answer.